In this video, we will explore the concept of upthrust in fluids. The term upthrust can also be referred to as buoyancy, and so the two terms are used interchangeably. Let's begin by briefly talking about the idea of fluids. In science, the term fluid refers to both liquids and gases because their content can easily flow. So upthrust in fluids refers to upthrust in both liquids and gases. The concept of upthrust plays a major role in flotation in fluids. In our tutorials on flotation, we attributed a body's ability to float or sink in a given fluid only to its density. We established that for a body to float in a fluid, its density must be less than that of the fluid, and for a body to sink in a fluid, its density must be more than that of the fluid. Though this fact is very true, that is not all that takes place in floating bodies. According to Newton's third law of motion, to every action, there must be an equal opposite reaction. So, a body's ability to float in a fluid is not only due to its density, but also due to a reaction force acting in opposite direction, and this reaction force is what we call the upthrust force. So what is upthrust force? Let's explore. We know that as a body floats in a fluid, part of its volume is submerged and the other part remains above the surface of the fluid. The fraction of the body below the liquid goes there by a downward force. This downward force may be referred to as the weight of the body, which we usually represent by capital W. So, according to Newton, another force of equal magnitude must act in opposite direction. In fluids, this force, which acts in opposite direction on bodies, thereby helping them to float, is what we refer to as the upthrust force. This means that for a body to float in a fluid, the weight of the body or the weight force of the body must be balanced by the upthrust force, and this makes the body to be in equilibrium. We remember from the concept of density and flotation in previous videos that when a body is immersed in a fluid, it displaces a volume of the fluid which is equal to its volume. What we must know in addition to this fact is that the weight of the volume of the liquid displaced is equal to the upthrust on the body. So let's write a simple mathematical equation here. That is, upthrust on the body is equal to the weight of the liquid displaced. Let's label this as equation 1 because we will refer to it in the course of our tutorial. One of the effects of upthrust on a body in a fluid is that it results in a reduction in the weight of the body. This means that the weight of the body before it was immersed in the fluid, which we call the weight in air, represented by WA, is always greater than the weight in the fluid, represented by WL. The difference in the object weight in air and the weight in the fluid is called the apparent loss in weight. And one thing that we have to take note is that this apparent loss in weight is also equal to the upthrust on the body. So now let's write down some relationships. Apparent loss in weight of a body is equal to the weight in air minus the weight in the fluid. In terms of symbols, the apparent loss in weight will be equal to WA minus WL. And since we know that the apparent loss in weight is equal to or the same as the upthrust on the body, we can write that upthrust on the body is equal to weight in air minus weight in the fluid. Let's label this as equation 2. Now let's compare equation 1 and equation 2. By comparing equation 1 and equation 2, we could see that equation 1 is equal or the same as equation 2 because both are an expression of the upthrust on a body. So we can equate the two of them. We can write that the weight of the fluid displaced is equal to the weight in air minus the weight in the fluid. And we know from flotation that the weight of the fluid displaced will be equal to the density of the fluid times the volume of the fluid displaced times the acceleration due to gravity. So we can finally arrive at the relation that the density of the fluid multiplied by the volume of the fluid displaced multiplied by the acceleration due to gravity is equal to the weight of the body in air minus the weight of the body in fluid. All that we have discussed so far can be put in a single sentence, and this single sentence is called Archimedes' principle. So what does Archimedes' principle state? Archimedes' principle states that when a body is partially or totally immersed in a fluid, it experiences an upthrust, and this upthrust is equal to the weight of the fluid displaced. The concept of upthrust in fluid can be used to determine the relative density of both solids and liquids. So let's look at how to find the relative density of a solid using upthrust or Archimedes' principle. The relative density of a solid is the ratio of the upthrust on the solid in air to the upthrust on the solid in water. Mathematically, we can write that relative density of a solid is equal to upthrust on the solid in air divided by the upthrust on the solid in water. And we know that the upthrust on a body is the difference between the weight in air minus the weight in a fluid. And since we don't have any fluid, so to speak, in air, the upthrust on the body in air is the same as the weight of the body in air, which we represent by WA. But the upthrust on the solid in water will be the difference between the weight in air minus the weight in water, which you are going to get WA minus WW. So we can write in terms of symbols that the relative density of a solid is equal to WA divided by WA minus WW. Now let's talk about the relative density of a liquid. The relative density of a liquid is the ratio of the upthrust on a solid in the liquid to the upthrust on the solid in water. So we can write that the relative density of a liquid is equal to upthrust on solid in the liquid divided by upthrust on solid in water. You know, we cannot find upthrust without putting or immersing a solid in a liquid. And so even though we are talking about the relative density of the liquid, because we are dealing with upthrust, to find the relative density of the liquid, we have to use a solid. So we can write this in terms of symbol as relative density of liquid is equal to WA minus WL. That is the upthrust in the liquid. So WL represents weight in the liquid divided by WA minus WW. That is weight in air minus weight in water. So let's differentiate between the relative density of a solid and the relative density of a liquid when we are using Archimedes' principle or the principle of upthrust. Now let's brainstorm a little. We know that if the density of an object is greater than that of a fluid, it will sink in the fluid. We know that it will float on the fluid when its density is less than that of the fluid. The question for brainstorming is that, what if the density of the object is equal to that of the liquid or fluid in which it floats? What do you think will happen? Well, it will float perfectly. This means that it will float with no part of it being immersed in the fluid. Having known this, the next question for brainstorming is that, what if the density of the object is far less than the density of the fluid in which it is immersed? The logic here is that if a body's density is greater than that of a fluid, it will sink in it. If its density is less than that of the fluid, it will float on it. But if its density is more or less or far less than that of the fluid, then it means it must come above the surface of the fluid more than it floating. In other words, it must be elevated above the surface of the fluid. And this is more practical and realistic in gases. And so an example we are going to use is the hot air balloons. Hot air balloons are able to float and travel across the sky for a long period of time before it comes back to the ground. What is the principle behind the operation of hot air balloons? Alright, let's discuss. The density of hot air balloons is far less than that of the surrounding air. As a result, the weight of air that it will displace is greater than its own weight. According to Archimedes' principle, the weight of air displaced is equal to the upthrust force. So the resultant buoyant force will be greater than the weight of the hot air balloon. And this provides the lifting power of the balloon traveling across the sky. Now let's conclude this session by solving two problems. In our next tutorial, we are going to solve more problems. Question 1. A metal weighs 20 newtons in air, 12 newtons in water, and 14 newtons in kerosene. Calculate the relative density of the metal and of the kerosene. So let's put down the details of the question so that we can analyze it well. First of all, we have the weight of the metal in air, which we are representing by WA, is equal to 20 newtons. The weight of the metal in water, which we are representing by WW, is equal to 12 newtons. And the weight of the metal in the kerosene, which we are representing by WL, is equal to 14 newtons. So you have been asked to first of all calculate the relative density of the metal. So as you have already established, the relative density of the metal will be equal to the upthrust on the metal in air divided by the upthrust of the metal in water. So writing this in symbols, we are going to get WA divided by WA minus WW. Substituting in the values, we are going to get 20 newtons divided by 20 newtons minus 12 newtons. So when we simplify this, we are going to get 2.5. So the relative density of the metal is 2.5. Now the second part is asking us to find the relative density of kerosene, which is the liquid. So here, the relative density of kerosene will be equal to upthrust of the metal in kerosene divided by upthrust on the metal in water. Writing it in symbols, we are going to have WA minus WL divided by WA minus WW. Substituting the figures, we are going to get 20 newtons minus 14 newtons divided by 20 newtons minus 12 newtons. By computing this on our calculators, we are going to get 0.75. So the relative density of the kerosene is 0.75. Now let's take our second question. A metal block weighs 1.8 newtons in air and 1.6 newtons in water. What will be its weight in a liquid of relative density 0.65? So three details have been given in the question. First of all, we have been given that the weight of the block in air, WA, is equal to 1.8 newtons. Then the weight of the block in water, WW, is equal to 1.6 newtons. And the relative density of the liquid, RDL, is equal to 0.65. So we know that the relative density of the liquid will be equal to upthrust on the block in the liquid divided by upthrust on the block in the water. Now let's write this in symbols. So RDL is equal to WA minus WL divided by WA minus WW. Substituting in the figures, we are going to get 0.65 is equal to 1.8 newtons minus WL, because we don't know what it is, and that is what we are finding, divided by 1.8 newtons minus 1.6 newtons. Simplifying this, we are going to get 0.65 is equal to 1.8 newtons minus WL divided by 0.2 newtons. Now let us do cross multiplication. We are going to get 0.65 times 0.2 newtons equal to 1.8 newtons minus WL. And this is going to give us 0.13 newtons is equal to 1.8 newtons minus WL. Making WL the subject, we are going to get WL is equal to 1.8 newtons minus 0.13 newtons. And finally, we are going to get 1.67 newtons. Thank you so much for sticking with us to the end of this video. Please remember to subscribe, share, and like our video. Thank you.